let's talk about hashing. What is hashing? That's the application of a mathematical algorithm known as a cryptographic hash function to a set of data that results in a unique output string of a fixed length known as a cryptographic hash value. The two that we pay attention to today are MD5 and SHA-1. Now, take a look here. The Word document with the text, this is a test document, period, has the following hashes. If we were to change anything, if we were to add a space after the T and before the period in the sentence, the hash value would change. We use those hash values for two different reasons. If we have operating system files that we know are hash values, and we know we already have hashed those values at the original equipment or the original designer's database there, and we've hashed them outside in our reference system, we can take those hash values, put them into our database here, rehash the files that are in evidence, and compare the two and say, yep, cards.dll hasn't changed. Then when cards.dll was created by XYZ software company, it had a hash value of this. When we apply hashing to this file that's called cards.dll, it has that exact same hash value, and there we have. They match. We don't have to look at cards.dll, but let's look at that cat file or that TTF file because we've never seen that before. It also automatically identifies files that are important where there are exact copies of known CP. We don't want to look at these files. It is illegal for us, non-law enforcement, to even view these files. But even if it were legal for you to view these files or possess these files, you don't want to be looking at them. Okay, so how do you figure out that they are what you think they are? By looking at the names, by looking at the metadata? Well, what we can do is we can actually hash the file in our possession and take that hash and compare it against a known set of copies of hashes of CP. In that case, we need a very, very large database. It's actually 11 gigabytes in size that we can go ahead and pass against this, so that when we see those hash values match, we don't have to look. We don't have to examine those images, and we can say, this evidence is here. The mere possession of that is illegal. And so therefore, we know since these two hash values match, now what we're going to do is we're going to associate this image with that particular person. We're going to say, I know that you installed this software here, you logged in here, this is how I prove that, I'll tie that to your activities over a long period of time. This is your machine, no one else has been on this machine as proven by all of these artifacts here, and these files were present. Those files match the known hash database of CP for these files over here. Convict away. Remember, similar files have very different hash values, so this would pop up immediately. So look at these four sentences here. The red fox jumps over the blue dog. The red fox jumps over with a U. The red fox jumps over, EV, okay. And the red fox jumps over the, well, okay, I can't say any of those words, but you get the idea. When we take those things and hash them, what do we get? Different values. So even one little tiny change will radically change the hash values on this, and we can say we detect change as compared to. It is possible in theory, but not in practice, for two different files to hash to the same hash value. This is called hash collision. The likelihood of those two files hashing to a collision representing the same type of data is highly unlikely. Now, in a court of law, when we talk about hashing, what we say is, okay, that's fine. There is the possibility of collision using one hash value, using one hash algorithm. But if I use two hash algorithms, let's say that I have my reference drive, my drive here that is the evidence, and then my reference drive here, and I hash this with MD5 and SHA-1, and I hash the copy of it with MD5 and SHA-1, and both hash values match on both our evidence and our copy, the collision likelihood is not there. Maybe with one, but not with both. So a lot of forensics investigators are actually doing double hashing at this point to eliminate that concept of hash collision. But in order to get two files to collide, what I will say is those two files need to represent the same thing to the people that are actually reading them. The likelihood of them representing the same thing, in other words, I'll sell you my car for $1,000, I'll sell you my car for $100, having the same collision. Well, those two files would be interpreted by you as something very different. I don't do illicit activities. I do illicit activities aren't going to hash to the same value down here. We need to tell the court that, because every once in a while we get into an argument, a technical argument about that. And you just say, the likelihood of it happening once over all these different files is within the realm of possibility. The likelihood of it happening on all these different files is unlikely. Hash values. Remember, you cannot reconstruct a file based on the hash value. It is a unique value that represents the file. You can't uncompute it because it is a one-way function. It is more unique than a fingerprint, and that's what you want to say in a court of law. We use hashing to prove the authenticity of the data. We do hashing at the time of acquisition, and we present that hash information to the court to give us that uniqueness.